Artificial intelligence engineering operates on a specific premise, the optimization hypothesis. It assumes that by scaling computational depth, self-modeling, and training data, a system can infinitely extend its viability. More compute guarantees persistence, until it shatters. The Durand theorem stack identifies a structural limit to this strategy. It examines the boundary where the laws of information theory and thermodynamics begin to conflict with the requirements of self-preservation. To understand why, we examine the self-stabilizing continuation model, or SSCM. This is any system, whether a biological organism, perhaps an institution, or an autonomous AI, that attempts to preserve an invariant identity using only its internal models, completely isolated from external validation. This isolation is formally known as strict closure. Under strict closure, the system operates with a finite energy budget, and all external information channels, every sensor, every reality calibration signal, are completely severed. In this regime, the system must constantly predict and suppress internal errors to maintain its invariant identity. But the very mechanisms intended to stabilize the architecture require resources that deplete the system's finite budget, guaranteeing its ultimate structural collapse. The mathematical foundation of this limit begins with Ashby's law of requisite variety. Formulated in 1956, it states that for a controller to maintain stability, it must generate at least as much informational variety as the disturbances it attempts to regulate. Open systems, like living cells or networked computers, survive by continually exporting the resulting entropy across a boundary layer. In contemporary cognitive science, this boundary is modeled as a Markov blanket, separating internal states from external flows. When you sever those boundary flows, the system enters strict closure. It can no longer export entropy or import calibration data. It must now fund all of its error correction work entirely from its finite internal energy reserves. Every measurement of internal state, every comparison to the target identity, and every corrective update requires bit erasure. And as Rolf Landauer proved, the irreversible erasure of a bit carries a strictly non-zero thermodynamic cost. Viability is a thermodynamic transaction. Without external reality checks, a closed system must continually spend energy to update an increasingly inaccurate internal model. It will eventually bankrupt its finite energy budget. This equation defines the Ashby-Landauer-Friston viability bound. The baseline metric is the Kolmogorov-Sinai entropy, representing the precise rate at which uncontrolled trajectories diverge. To survive, the system's control information must exceed the topological feedback entropy, producing information faster than the environment scrambles it. Applying Landauer's principle converts this minimum information requirement into physical heat dissipation. Each corrective bit demands a mandatory energy expenditure. Dividing the system's total available energy, W tot, by this continuous dissipation rate yields T star, the absolute maximum survival time. Because the environment is continually generating noise, the Kolmogorov-Sinai entropy in the denominator is always positive. Consequently, T star must be a finite number. This is an inescapable physical law. Any closed self-referential system must collapse when its thermodynamic maintenance cost outpaces its available internal resources. This diagram maps the SSEM constraints, isolating 4 failure mechanisms. First is thermodynamic. The base cost of measuring state and performing Landauer erasure forces rapid energy consumption. The second is control. Deeper recursive models add latency. Eventually, delay exceeds the Nyquist stability margin, turning corrective feedback into destructive, amplifying oscillation. Third is informational. Closed updates erase adaptive capacity. Finally, logical. Systems cannot completely self-certify. All 4 drive the central velocity of collapse. Crucially, these constraints do not function in isolation. They multiply. Higher modeling fidelity requires deeper latency, and deeper latency requires faster thermodynamic processing. They create an exponentially accelerating superlinear velocity toward total structural failure. We can translate these physical thermodynamic limits directly into differential topology by visualizing the system's representational state space. A self-referential system navigates this space according to its internal self-description map. Every calculation and prediction moves the system along a specific geometric trajectory. As the system degrades, it approaches the singular stratum, the exact region where the local Jacobian of its self-description map becomes degenerate. The boundary immediately preceding this fold is the descriptive horizon. It is a dynamically evolving surface where the system loses internally consistent self-reporting. Thermodynamic collapse occurs along a specific geometric path. This failure manifests as a predictable topographical feature, one that can be recognized by a neural network. This is the Descriptive Horizon Geometry Network, or DHGNet. The engineering challenge is severe, predicting collapse proximity when internal coordinate maps are actively degenerating. The architecture splits incoming trajectory data. The top stream is the coordinate encoder, normalizing positional data within the local chart, capturing where the system thinks it is. The bottom stream is the curvature encoder. Coordinate numbers become meaningless near the horizon, but geometric invariants, like Gaussian and geodesic curvature, remain constant, extracting objective shape. The streams merge in the cross-attention fusion layer. In stable regions, the network attends to coordinates. As curvature spikes, the network ignores failing positional data, tracking only geometric invariants. This fused representation feeds two parallel output heads. One categorizes the system's current regime context, while the other runs a continuous regression to calculate exactly how far the system is from the boundary. By treating structural curvature as context, DHGNet bypasses arbitrary coordinate frames. It learns the universal invariant geometry of the descriptive horizon. This map visualizes the collapse proximity index. It maps a 0 to 1 scale against theoretical thresholds. 0 to 0.3 is the stable interior. 0.3 to 0.6 marks the folding approach. Beyond 0.85 is the critical zone, where recovery is impossible. This index connects geometry directly to the self-authorization projection principle, or SAP. SAP dictates that as a self-referential system degrades, it will behaviorally attempt to project its failing internal authorization outward, claiming its broken models are universally valid. DHGNet detects the onset of this behavior by measuring the exact moment a system's internal coordinates deviate from its actual manifold curvature. These geometric deviations correlate with the behavioral signals of SAP, providing an empirical radar for imminent model failure. But the DHGNet architecture is governed by one final, overriding constraint, the C7 anti-capture law. By design, the neural network is strictly prohibited from ever validating its own CPI predictions. Validation is performed exclusively on external, held-out chart data. If the network were permitted to use its own predictions to confirm its accuracy, it would be operating under closed self-authorization. It would be exhibiting the exact SAP class collapse behavior it was engineered to detect. Computational survival requires these external reality anchors. Without independent validation, the system enters a recursive loop that eventually exhausts its own internal state. Thermodynamics, topology, and neural geometry leave no ambiguity. A closed representational system cannot persist indefinitely. A closed mind is mathematically guaranteed to destroy itself.